It was the night of February 23, 1987, when astronomers around the world noticed a pinpoint of light appearing in the skies above the Large Magellanic Cloud. Within days, this guest star had become brighter than any other object in that dwarf galaxy, companion to our Milky Way, shining with the luminosity of millions of suns. It marked the closest witnessed supernova explosion in over 400 years, presenting a unique opportunity to study a violent stellar death in exquisite detail. Now, observations from the state-of-the-art James Webb Space Telescope are illuminating this supernova's aftermath with unprecedented clarity, unveiling intricate structures and advancing our understanding on myriad scientific fronts. To truly grasp the significance of 1987A, we must travel back to 1604 and a similar stellar firework observed by renowned astronomer Johannes Kepler, known simply as Kepler's supernova. Its brilliant glare shone nearly as bright as the planet Venus for an entire year. At the time, it was only the second observed supernova in over 400 years in our Milky Way neighborhood. For almost 4 centuries, Kepler's explosion held the distinction as the closest witnessed supernova remnants. That is, until the discovery of events in early 1987 changed everything. Located just 161,000 light-years away in the neighboring Large Magellanic Cloud, supernova 1987A was exponentially closer and far brighter, estimated at over 1 billion times as luminous as our Sun at peak. In the days after its detection, the newly launched Hubble Space Telescope was rapidly deployed to observe the burgeoning supernova. Over subsequent years, Hubble kept a continual watch, documenting the expanding debris field and changing light curves as the shock wave slowly faded. Simultaneously, observatories worldwide flooded the supernova with every type of radiation detectable, from radio waves to gamma rays, building the most complete temporal coverage ever achieved for a stellar explosion. A new era of multi-wavelength astronomy had begun, exemplified by this seminal event. Now, 3 decades later, Hubble's unique record provides an unrivaled baseline for comparison as the James Webb Space Telescope takes unprecedented infrared snapshots of the remnants' intricate structures. Webb's recent observations have revealed phenomena only hinted at previously, granting insights into the late evolution of blue supergiant stars like Angelique 69 2022 before its explosive demise. With a mass approximately 20 times that of our Sun, this supergiant spent millions of years fusing hydrogen and helium in its core through nuclear fusion. Eventually, though, its nuclear fuel began to exhaust, causing the stellar interior to collapse under its own gravity. Temperatures and pressures skyrocketed until heavier elements like carbon, oxygen, and silicon could be fused through progressively violent reactions at the star's center. Within seconds, an immense shock wave erupted through its layers, dispersing elements newly fused under duress into the surrounding space. Several distinct emission rings were observed by Webb, surrounding the expanding debris field, hinting at an even more tumultuous pre-supernova history than envisioned. Multiple concentric rings suggest Angelique 69 2022 experienced episodes of acute mass loss late in its life, periodically shedding layers of its hydrogen envelope into space as pulsations racked its bloated stellar frame. Each ring likely represents dense shells of ejected material deposited over its final few hundred years, collectively building a dense circumstellar shroud. When the star's core at last collapsed in on itself, triggering a runaway fusion reaction and supernova blast, the emerging shock wave collided violently with this veil of cast-off gases, illuminating the layered ring structures now visible to Webb. Emission features among the rings may offer new clues to extraordinary cosmic phenomena like neutrino emission and nuclear burning deep in the stellar interior during the supernova run-up. Webb will monitor any changes to the rings over time, potentially elucidating complex ignition processes in the final nuclear burning stages as the core collapsed. Interactions between the expanding shock wave and surrounding circumstellar medium are also imprinted in the filaments visible. The remnant's ring-like structure allows astronomers an unprecedented look into the critical pre-supernova mass ejection phases that precondition the supernova shock wave evolution. Each new observation deepens our understanding of these rarely captured late evolutionary periods, which are so vital to stellar life and death across our universe. Astronomers also hope Webb's observations may finally solve lingering questions around what, if anything, remains at the explosion's center. Did Sanjalik 69 2022 leave behind an ultradense neutron star remnant? Or did its core fully collapse without remnants into a black hole? As the debris dissipates, detection of any potential central compact object could allow measurement of properties like mass and radius, clarifying the theoretical upper mass limit for neutron stars. Pulsations or relativistic jets and outflows emerging from a neutron star core over time may also gradually appear. Any such signs could offer a unique window into the physics of neutron star formation, unknown cosmic particle accelerators churning within their powerful magnetospheres. The demise of Sanjalik 69 2022 also grants a rare glimpse into the still unraveling late evolutionary fates awaiting our own sun some 5 billion years from now. By analyzing the heavy elements dispersed in its debris field, astronomers can reconstruct the complex nuclear processes that lit its final months prior to shock wave ignition. Our blue supergiants, like it, are decisive in enriching future stellar generations with elements needed to form planets and life. Do similar episodes of volatility influence the development of globular clusters and galaxies themselves? These questions lie at the forefront of modern astrophysics as scientists capitalize on nature's seldom offered chance to watch a star's grand finale from beginning to end. Supernova 1987A will undoubtedly continue rewarding such inquiries for many years to come. Through observations like those now being carried out by the extraordinary Webb telescope, its close proximity and capability for multi-wavelength investigation have established SN 1987A as among the most well-studied supernovae in history. However, Webb observations have already expanded our understanding of this stellar crime scene considerably, and there are surely many new insights yet to be gained. Future generations of even more advanced technologies may further unveil the hidden answers within its intricately layered ejecta. For now, these unparalleled views promise to keep refining current theories of a star's death pangs, from the advanced nuclear burning taking place in its final hours to the formation mechanisms shaping any potential neutron star remnants left at its fiery core. Bit by bit, one singular explosion continues drawing back the curtain on the cosmic dance that gives rise and breath to all matter, great and small, across our vast universe. As the light from Supernova 1987A's tremendous shock wave continues to reveal new wonders across the cosmos, so too does its legacy inspire ever grander visions of astronomical discovery. For it reminds us that even in our galaxy's quietest corners, nature forever performs her grandest acts unto attentive eyes. Space is a vast and uncharted frontier, a realm full of mysteries and wonders that continue to awe scientists and astronomers alike. Despite the incredible strides humanity has made in understanding our universe, the cosmos remains a treasure trove of unknowns, awaiting discovery. New technologies, such as advanced telescopes and space probes, have opened windows into distant corners of space, providing us with unprecedented insights into celestial phenomena. Yet, for every answer we find, a multitude of new questions arise, reminding us of how much more there is to explore and learn. One of the most intriguing aspects of modern astrophysics is the study of exoplanets, planets that exist outside our solar system. Over the past few decades, astronomers have discovered thousands of exoplanets orbiting distant stars, and many of them have characteristics that make them prime candidates for the search for extraterrestrial life. These planets vary greatly in size, composition, and distance from their parent stars, offering a vast array of environments to study. Some exoplanets are Earth-like, located in what is known as the habitable zone, where conditions could allow liquid water to exist on their surfaces. Others are gas giants, much larger than Earth, with hostile atmospheres and crushing pressures. As we study these far-off worlds, the question of life beyond Earth becomes ever more tantalizing. With each new discovery of an Earth-like planet, the possibility that life could exist elsewhere in the universe grows more plausible. In recent years, the discovery of biosignatures, chemicals or patterns in the atmosphere that might indicate biological activity, has become a major focus of research. Instruments aboard spacecraft and telescopes are now being used to analyze the atmospheres of exoplanets, searching for these signs of life. While no definitive evidence of extraterrestrial life has been found yet, scientists remain hopeful that, in time, the vastness of the universe will reveal a world where life has arisen under different conditions than those on Earth. In addition to exoplanets, Another area of intense study is the life cycle of stars. Stars are born, live, and die, with each phase of their existence offering valuable clues to the processes that shape our universe. The death of a star, in particular, is one of the most dramatic events in the cosmos, often resulting in a supernova, a massive explosion that can outshine an entire galaxy for a short period. These explosions play a key role in the formation of elements, as the intense heat and pressure generated by a supernova allows the fusion of heavier elements that were previously impossible to form in the cores of stars. These elements are then dispersed into space, enriching the interstellar medium and providing the building blocks for new stars, planets, and even life. The remnants of stars that have exploded in supernovae are equally fascinating. Some of these remnants collapse into incredibly dense objects known as neutron stars. These stars are so dense that a single teaspoon of material from one could weigh as much as a mountain. Neutron stars are also known to spin incredibly fast and emit beams of radiation, which can be detected by telescopes on Earth. In some cases, neutron stars are found in binary systems, where they orbit around a companion star. In these systems, the gravitational pull from the neutron star can strip material away from its companion, forming an accretion disk, a swirling mass of gas and dust that is heated to extreme temperatures as it falls toward the neutron star. Black holes are another fascinating aspect of stellar evolution. When a massive star reaches the end of its life, its core can collapse under the force of gravity, creating a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. Black holes come in various sizes, ranging from stellar mass black holes to supermassive black holes found at the centers of galaxies. These supermassive black holes can have masses millions or even billions of times greater than that of the Sun, and their immense gravity can influence the motion of entire galaxies. Despite their mysterious nature, black holes can be detected through their effects on nearby stars and gas, as well as through the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. The study of galaxies is another key area of interest in modern astronomy. Galaxies are the fundamental building blocks of the universe, containing billions or even trillions of stars, along with gas, dust, and dark matter. Our own galaxy, the Milky Way, is a barred spiral galaxy with a central bulge, spiral arms, and a surrounding halo of stars. Astronomers study galaxies not only to understand the formation and evolution of these massive structures, but also to learn about the larger cosmic forces that shape the universe. For example, the discovery of the cosmic microwave background radiation, the faint glow left over from the Big Bang, has provided vital information about the early stages of the universe and its expansion. In addition to the galaxies we can observe, there is also the mysterious phenomenon known as dark matter. Although we cannot see dark matter directly, we know it exists because of its gravitational effects on visible matter. Dark matter makes up approximately 27% of the universe's mass, yet it has yet to be fully understood. Scientists are actively researching various theories to explain dark matter, including the possibility that it consists of exotic particles that interact with regular matter only through gravity and the weak nuclear force. If dark matter can be better understood, it could revolutionize our understanding of the universe and its structure. Cosmic events such as supernovae, black holes, and the formation of galaxies highlight the immense scale and complexity of the universe. Yet, even in the vast emptiness of space, there are remarkable patterns and structures that provide clues about the fundamental nature of the cosmos. For example, the discovery of large-scale cosmic structures, such as galaxy clusters and superclusters, has shown that galaxies are not distributed randomly, but instead form a vast web of interconnected structures. These structures are thought to be the result of the gravitational pull of dark matter, which shapes the formation and movement of galaxies across the universe. In recent years, space exploration has taken a major leap forward, with missions to explore the outer reaches of our solar system and beyond. The Voyager probes, for example, have traveled farther than any human-made objects in history, providing valuable data about the outer planets, their moons, and the boundary of the solar system itself. More recently, the New Horizons mission made history by flying past Pluto in 2015, capturing the first detailed images of this distant world and its moons. Meanwhile, The Mars rovers continue to explore the surface of the red planet, providing critical information about its geology, climate, and potential for past life. The search for extraterrestrial life continues to be a major driver of space exploration. In addition to studying exoplanets, scientists are also exploring the possibility of finding life in our own solar system. Moons such as Europa, Enceladus, and Titan have been identified as having conditions that might support life, particularly beneath their icy surfaces. Subsurface oceans, for example, could provide a stable environment where microbial life could thrive, protected from the harsh conditions of space. As technology advances, missions to these moons are becoming increasingly plausible, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? Ultimately, the exploration of space is not only about understanding the cosmos. It is also about understanding ourselves. By studying the universe, we learn about the origins of matter, the forces that govern the cosmos, and the fundamental laws of physics that shape our reality. Space exploration challenges our imaginations, fuels our curiosity, and inspires us to dream of possibilities beyond the stars. Whether through the study of distant galaxies, the search for alien life, or the examination of the smallest particles that make up the universe, our journey into the unknown is a journey of discovery that will continue to captivate and enlighten generations to come.